So good afternoon, everyone. So we're going to get started. I'd like to introduce Dr. Alyssa Dalby. She's a research engineer in the Deep Submergence Laboratory at Woods Hole, but also she's a UNH alum who graduated with her PhD in 2021, and she's also formerly from my lab. So Alyssa's a good friend to me as well. Her dissertation work spanned the research areas of autonomous decision-making, mission planning, path planning, and test and evaluation methods for autonomous systems. And since beginning at HUI, she's participated in over 10 expeditions working with deep sea vehicles, some of which you'll hear today, including Nereid Under Ice, Sentry, Leo, Orpheus, and Alvin. And while on shore, she's involved with the development of robotics, software tools, integration of remote operations, performing data analysis, and modeling and simulation of fiber optic tethers for subsea applications. So let's give a warm welcome to us.
Thanks, Hannah. It's nice to be back here. I'm seeing some familiar faces. So I'll be talking about two expeditions I just returned from Greenland to American Samoa, using two vehicles Nereid Under Ice, a hybrid ROV, and also AUV Sentry. So first I'll give an intro to the Deep Submergence Lab, which is the lab I am part of. And then the first part will be Nereid Under Ice and the work in Greenland, before I move to the AUV Sentry work off of American Samoa this past summer. So just some various pictures from those trips there. Two very different landscapes. I also have a slide of how I got from one place to the other in like 3 days. It was not easy. So Woods Hole Oceanographic, we have about 1,000 employees and also joint program students for an MIT HUI PhD program. We're independent nonprofit, so a lot of our funding comes from science sources such as NSF, but also ONR. And so we're sort of a blend of academic, government, and independent. There's 5 different research departments. So I'm part of the Applied Ocean Physics and Engineering, which is what Deep Submergence Lab falls under. But there's also biology, geology, chemistry, and physical oceanography departments as well. So the Deep Submergence Lab, we have a variety of unique custom-built vehicles. So in the top left, we have Mesobot. That is a mid-water level vehicle. Has actually worked with Drix, if you're familiar with that vehicle here from CCOM, several times. Nereid Under Ice, or what we call NUI, in that top center picture, which is what I'll be speaking mostly about this afternoon. The bottom left is Clio. This is sort of like a tetherless CTD and takes biogeochemical samples and has some unique chemical sensing and in-situ sampling capabilities. Orpheus is a full ocean depth vehicle, small scale, supposed to be lower cost, so you can operate these in fleets. There's 2 of those vehicles currently. Sentry is the other vehicle I'll speak to this afternoon, and that's housed in the National Deep Submergence Facility, which also has human-occupied Alvin and our large-scale ROV Jason. Both Alvin and Jason are 6,500 meter railing vehicles. So Nereid Under Ice is a hybrid vehicle, and we call it hybrid because it can operate both as an autonomous underwater vehicle and as a remotely operating vehicle. And this is because we have a lightweight fiber optic tether, which I'll speak to on the next slide. It's 5,000 meter depth railing, and the unique capability of this vehicle to work under ice is that it can travel very far horizontally. So as we're in the ice, we have to actually chase the ship as we drift in the ice. So this horizontal capability is huge. Has onboard power. There's no power through our fiber optic tether. So we usually see about 10 to 12 hours of endurance depending on what we're doing, sampling, what sensors we're running. We also have a manipulator arm, so we can take push cores and other samples. So this fiber optic tether is lightweight and it's actually bare fiber, no armor. So that top picture there shows just the diameter of that fiber compared to human hair. So very thin. If you look at it, you would not think it could survive. But we often see full dives where we have no issues or loss of comms. So we operate in a depressor tow body configuration. So this top right picture, that top device there we call the depressor. And inside of that, when we deploy the vehicle, is the tow body. Both of these have fiber optic canisters, so what that bottom image looks like there. And each of those have 20 kilometers of this fiber. And once we reach a certain depth, these two separate, and they are able to dispense this fiber and decouple both the ship motion and the vehicle motion. So we have an umbilical on that vehicle to the tow body. So as that maneuvers, we can also spool out tether. We're able to actually monitor this tether health throughout the dive through optical time domain reflectometer traces. And this allows us to see bends or any other imperfections in the tether across the entire tether. So oftentimes we'll know when the tether is about to break before it actually breaks because we can see it degrade in performance. Some previous work with Nereid Under Ice have been part of the past few years. We've been on board Nautilus twice, both in 2021 and 2022. Also working with Drix on one of those cruises. So that was on EV Nautilus. And while we were not under ice, we were actually off of Hawaii and California. The vehicle works very well as a test platform because we can operate both as an AUV and ROV. Last summer, we spent 6 weeks on the Polar Stern, which is a German icebreaker up in the Arctic. This is a very cool trip where we actually got to see Nui do its thing under ice. So here we see one of the recoveries. We have to find a pool of water to actually come up in, which can be a challenge with that much ice cover. So that was not a very large pool, but we found it and were able to recover there. And we were at what was called the Gackle Ridge, so about 4,000 meters depth, where we were at a series of hydrothermal vents, one of which you see in that bottom picture. So this most recent summer, back in August, we were out in Greenland with Chief Scientist Dr. Jenny Catania from the University of Texas. So I know Larry or Dr. Mayer gave a talk last week on his Greenland experience. And we were actually on the southwestern side. I think he was more north than us, but I think almost at the same time. So he probably gave some preliminary Greenland facts here. So what we were looking for is quantifying the rates of processes contributing to the sediment buildup at the termini of these outlet glaciers. So these scientists really care about the moraines and how they're produced. So looking at how these processes contribute to sediment mass balance within moraines at these glacier termini, and also just in general link these processes to the drivers such as the ice sheet, climate, geometric, etc. So really they're looking to provide a more realistic description of how these glaciers vary over time and better inform their future models. So we were supposed to go to 3 different fjords in that southern part of Greenland. We actually only ended up making it to one of those 3 due to the ice coverage. So the ship we were on was not ice rooted, so we could not actually break ice. But we were able to have 8 dives at Kangalusak Fjord, which is this bottom right one here. So we spent most of our time there, and it ended up working out pretty well because we were able to get a more comprehensive survey of the entire area. So from a science perspective, there's a lot of sediment processes going on here, which the scientists understand way more than I do, but just from a high level view, where that number 2 is, this is just a depiction of what it should have looked like with Nui being tethered to the ship, taking some measurements, and some of the sediment flows in and out, and combined make these moraines that are supposed to act as sort of speed bumps with how glaciers move. And also with the glacier flows, we were also taking some profiles of the currents coming out of the glacier as well. So we were on an Irish vessel called the Celtic Explorer. Home port is Galway, Ireland. Carries up to 35 people and about 65 meters in length. And it's actually designed more for fisheries research. So it's actually a very, very quiet ship. Engines running, you couldn't really hear much, which is not what is typical of the research vessels we're on. So it was an ideal environment for some of their own multi-beam surveys, and they were also doing a lot of seismic and other things that had a lot of acoustics involved. So we pack on as many sensors as we can onto NUI. So we have a down-looking multi-beam. Along with this trip, we newly integrated a sub-bottom profiler. In that bottom left, we have a fluorometer at the front of the vehicle. And we also have a downward-looking and upward-looking DVL. So this is usually a downward DVL is standard, but the upward-looking helps us when we're under ice, so we can actually localize ourselves under the ice as well. On the right-hand side here, we have our manipulator arm, which can take the push course and manipulate other items. We have some optical backscattered sensors. I think we had 3 of those on board. In the bottom here, we also have a forward multi-beam, so this allows our pilot to see what's in front of him and avoid any obstacles. Push cores, we had between 6 and 8 of those in the basket on any given dive. We have a high definition camera. So this is how we do most of our work on the seafloor with manipulation and push cores. We have a Niskin bottle for water sampling, listing RBR for more like turbidity particle analyzers, and also a sediment trap to bring up some sediment back to the surface. As I mentioned, we had multiple OBSs, so that was on the tail fin. We have a CCD on the front of the vehicle. Also, we have a 5K camera, also known as the Dan Cam, which is actually a GoPro inside a pressure housing and works surprisingly works really well, and we've used it on a lot of vehicles I work with, and can go almost full ocean depth. We also have a sideways facing Nortec ADCP. So this is what most of the oceanographers on board were using for their current profile data. So we were taking profiles both vertically and horizontally and getting the current profiles back. On some of the dives, we actually took our downward multi-beam and moved it sideways, as I'll show in a few slides, so we could actually map the face of the glacier. So there's a whole bunch of screens here, a whole bunch of arrows. So this is what our topside setup looks like. So depending on the ship, we integrate usually in one of their lab spaces, and you can have 10 to 12 screens at any given time. Top left, we have our navigation screen. So this is where we have previous bathymetry maps. The vehicle's position is plotted. And there's a bunch of tools we can use to better navigate the vehicle. Up top, those 2 arrows are the pilot and co-pilot GUIs. So this is where we control different sensors, turn things on and off, and there's some gauges so the pilot can be better informed of what the vehicle is doing. Usually we have a 4K camera installed as well. This took place of another sensor that we deemed more important. So usually there's a screen for that. Our Sonodyne USBL, so this is pretty standard. Most ships have a Sonodyne, sometimes it's a different brand. But this gives us our ranging bearing from the ship to the vehicle. In this case, it was a directional head, so we saw range out into about 1,000 meters from the ship in these cases. As I mentioned with the OTDR, so this is where our fiber optic cable traces were. So that was the screen we'd look at to make sure the tether was happy and was not having issues. We have a manipulator arm console. So this is how we pilot the arm. So it actually looks just like how the arm looks in the vehicle. So it has 7 joints that you can move independently. It can be a bit of an awkward exercise at first until you get used to it, to look at the cameras and things can be backwards. And, it's a skill that is definitely something that is needs to be practiced. And Victor did a great job this cruise on piloting and also manipulation in very low visibility conditions, which I'll get to also in a few slides. bottom left, so we usually have a screen, which is where we're looking at data streams in real time. We're also doing any troubleshooting, and also here we have some visualization of the multi-beam in real time. We also have the forward downward multi-beam. So this is what our pilot mostly used to navigate the vehicle. So he could see the glacier wall on one side, and then also any other obstacles. There are some cave-like features that we have to be careful not to get too far into because it'd be difficult to get ourselves. And if we had lost the tether in those situations, it would have been risky for the vehicle. In terms of navigation, we have some different communication pathways we use. Mainly, we use a HROV micromodem, 2 frequencies, so 2 transducers we use, a 10 kilohertz and a 3.5 kilohertz. So we have a 10 kilohertz, which we call a dangle inducer, which we drop over the side of the ship. Then we also have a 10 and a 3.5 on our depressor. So since the depressor is lowered from the ship, usually about 100 meters, it can help with a lot of the ship noise, and we can get better comms when we use the depressor transducers. As I mentioned, we also have a USBL with the directional head on this trip. There's also omnidirectional heads, which give you a bit more horizontal range. We have bi-directional communication, so we can give the vehicle commands, but also receive uplinks from the vehicle telling us basic health statuses. And this is assuming we have lost the tether. So AUV mode is when we really care about this acoustic communication. So usually with the USBL, it's about 1.5 kilometer or 1.5 times the water depth. That's how far we can hear from it. Micromodem, we can get pretty far, especially with 3.5 kilohertz. We've gotten up to 8 kilometers before with messages being sent back. They can be spotty, but it can be really important in these conditions where the ship doesn't want to get too close, that we have this horizontal range. A lot of it is noise dependent as well. Sometimes helps if we go as say all stop, so we stop all the thrusters and we can talk to the vehicle a bit better if we're having trouble. Also, the ship can turn off various sensors to help with this as well. So there's different ways in which we can better use that acoustic pathway depending on the ship and the situation. We use these, what we call range rings, which I have pointing out here. So we do get these pings from the acoustics that tell us range, but not direction. So we have these rings that can at least help us, along with the vehicle's dead reckoning of where it thinks it is, to sort of co-locate those, at least have a better idea of where the vehicle is to more precise location. So the vehicle dead reckons. So it thinks it knows where it is. Sometimes it doesn't actually know where it is, but we can also tell it where it is based off all this information that we can gather from the various acoustic pathways and other sensors. Then what we do is after the dive, we take the USBL data and the dead reckoning data, and we fuse this together to give us a more accurate depiction of how it actually navigated during the dive. And this helps a lot with the multi-beam mapping. Yeah, that track line home, I'll speak to more of the mission planning, but this is just one of our ways in which we have contingency plans of what happens if things go wrong. So if the vehicle doesn't hear from us, it's supposed to go that track line to go home. So on to mission planning. So the contingency plans here are a bit different than your conventional AUV ROV missions, because we can't just come to the surface. As you can see with the ice coverage, that's just not an option. So we have, depending on the dive, we really have to think through what we want the vehicle to do in any given situation. It doesn't hear from us, or it knows it lost the fiber. There's different stakes and behaviors that it should undertake to deal with these. So, and we also need to be prepared for both missions involving ROV things, so manipulation, opening the doors, cameras, but also how we can best use the vehicle if we do lose the fiber. So typically what we'll do is have a multi-beam mapping mission lined up, ready to go in case we lose that fiber as a backup. There's a whole variety of tools we use too to give us better context of the environment and operating area. So We used a lot of SAR imagery or synthetic aperture radar for this trip to see changes over time to that glacier face and that red box. Then also each dive, we can come up with a plan of where our track lines we think should be. And also what we have in that bottom image is high resolution drone footage. So there's a drone team on this trip that would take these surveys before each dive, and were very helpful for the more dynamic changes in those glacier walls, dive to dive. So icebergs. So this picture here is just after we launched the vehicle. And you might be able to see Molly and Matt discussing why we now need to recover the vehicle. And this is because we had two large icebergs, or one iceberg that got split up, fall from the glacier right after we launched. So we had to immediately recover and the ship could back away to that really dynamic environment. So for a sense of scale, that glacier face from sea level to the top is about 60 meters or so. And the piece that broke off, so this was on the whiteboard the next day, is about 16, so 1.6 acres large. So just to think, it's a lot of football fields that fell off the front of that glacier. And ironically, we actually were delayed about an hour because we wanted more drone footage before we dove. So if we had to deploy on time, we would have been a lot closer to where that happened. So definitely just showing the risk of working in these environments, but also the reward of the data we get back is very well worth it. So here are some preliminary, so these are not clean maps yet. A lot of that processing is undergoing this fall with the science team. But we did very comprehensive maps of both the north face up top there, and then also the western face of that glacier there. And we used an orbit wide beam multi-beam sonar for these, and those are the multi-beam. We had both forward and downward orbit multi-beams. So when we would go with our side-facing multi-beam, we were taking using ROS, or Robot Operating System, the RViz tool, to visualize these point clouds in real time. And by seeing this data in real time, the science team was actually able to identify certain channels and areas of interest, so they could take these current profiles they were interested in. A lot of this side-facing multi-beam data is now being processed onshore as well. But as you can see, we saw some very cool features like this cave feature, which for scale, the bottom to top is about 200 meters. So that cave itself was about 100 meters in height. So this video is just showing the 3D-ness of that similar picture. And those caves, like I mentioned, are what we had to be careful not to navigate into, because also the currents were very strong pulling inward. So again, if we had lost the fiber, it would have been difficult to navigate the vehicle out of that cave. So as much as our pilot wanted to go into the cave, we had to make sure he stayed out. So in terms of sampling, so we took a series of push cores on this trip. We take them in transects from this, as close as we could get to the glacier face outwards. So as you can possibly see on the screen, there's a plume that you can see in the drone footage. There's a very dynamic area in terms of sediment, so visibility was very, very low. We could barely see the arms, whether the doors were open. We actually gained 60 pounds of sediment in the basket on one dive after we opened the doors. There was just so much sediment and mud flying around. So we actually had to drop our emergency weights just to make sure we were still positively buoyant if things went wrong and we had to surface. So we had to modify our sampling strategy. So we call these bumblebee cores. Usually what you do is you sit down on the seafloor, set yourself up nicely, grab your push core, take your push core and restow. Here we had to come up to an altitude where we could actually see the arm. This was usually around 70 meters from the seafloor. So we grab the push core, stage it outside the basket, overhanging the doors, and then we just descend. And through actually our multi-beam, we could see when we reached the seafloor and when we stopped moving. We assumed we took the push core. We come back up to where we could see again, and then we restow it. So not your typical push core, but it was what worked. And we actually were able to get towards roughly 40 meters from the face, which is likely the closest push core or any real sampling done to a glacier at this time. So in summary, we did 8 dives where launches equaled recoveries, which we like to say is what we want. We always want that number to be equal. 9 total push core samples, and then as I've shown, the high resolution mapping, both the seafloor and the glacier face. A series of horizontal and vertical profiles with the AZCP. We're also taking sub-bottom transects during these dives as well as our more standard suite of scalar data, CTDs, fluorometers. 2 things in the future we would like to look at, and the chief scientist is already scheming up, is extending our horizontal coverage using surface relays. So where the ship was a bit skeptical of how close they want to get due to how dynamic the environment was and how much ice cover was on the surface, whether we could get into some of these other areas that we were not able to get into this expedition by using the vehicles to travel further distances. And also try and implement some new autonomy strategies. There is some research out there for how to do this, for manipulating using sensors and autonomy in these low visibility environments. So there's an article published in The Guardian this past month on the trip. So the headline is there if you want to check it out. And before moving to the Sentry trip, just a shout out to our NUI team. So one of these, Somali is actually a UNH alum as well. So I work with quite a few UNH alums. So next up, how I get from Greenland to American Samoa in 3 days. So I was in 6 time zones, 6 flights between a Friday and a Monday. Started off in Nuuk, Greenland. I was actually the only one from the ship's crew or the science team to make it out for 2 or 3 days because Nuuk lost their security clearance with Denmark, and it's all a mess where you couldn't fly internationally from there. My first flight was domestic, so I got out. So then I went to Kanger, Greenland, Copenhagen, Reykjavik, Boston, back home for 36 hours, back to Boston, sat on the tarmac for 3 hours before making it to Honolulu, and then finally American Samoa. The flight path that looks something like that. But I made it, so that was definitely a bit stressful, but it worked out. So Sentry is a 6,000 meter rated vehicle, more designed for maneuverability. So we pre-program these missions, often surveys and multi-beam maps, some camera surveys as well. So this vehicle, we provide the full package. So everything from the initial mission planning to the processing of the data to the operations. This vehicle routinely operates with other vehicles, such as ROVs or HROV Alvin. And a lot of times with Alvin, Sentry will map all night, so it can provide a map for Alvin during the day. Endurance-wise, usually up to 30 hours is pretty standard. Again, depends on what sensors you have and power consumption. So this is about at 1 to 2 knots. And this vehicle is well known for being able to integrate new sensors and developmental sensors cruise to cruise, which isn't standard with some of these other vehicles. So we travel with 2 containers, a server van and a spares van. So we often operate on different ships, so have to integrate in various deck plans and lab traces with a team of 5. So we're a mixture of software, electrical, and mechanical. So again, we handle all aspects of the operations, from the mission planning to the maintenance, configuration changes, any troubleshooting that comes up, and we operate on these vessels at opportunity. So like this upcoming year in 2025, I believe we're on 4 or 5 different ships. Here's just a depiction of sentries and terminals. So we have a big chassis in the middle that has the batteries and some electronics. Has 4 different fins with 4 thrusters. A lot of the sensors and samplers are located on the bottom, and then a lot of the communications up top. We use syntactic foam for buoyancy. Both are images of sensor locations. So for this expedition, which is called NA 165, we're on EV Nautilus. So 68-meter vessel with about 35 science and operations personnel and 17 crew. So they have their own ROV Hercules, and their tow-sled Argus. So ROV Hercules is depicted in those 2 images there. And we are off of Paga, American Samoa, and for most of the month of September. This is our operation area. The star is Paga. The triangles were the ROV targets. And then the National Marine Sanctuary, where we also did some work, is in that blue box. We had a whole wide variety of science objectives this cruise. We first focused on 2 dives on the Samoan Clipper, the underwater cultural heritage site. This plane went down, I believe, in 1938, so quite a while ago. So we provided side scan mapping at about 20 centimeter resolution. Virtually no evidence of the plane. We saw some geologic features. We also had several dives detecting hydrothermal vents above the Vaiolulu seamount. So we provided also some comprehensive mapping of the summit crater, a lot more detail than some of the previous maps. We also had these dives for new algorithms for hunting these plumes, and this required data being pushed to shore in real time. So it'd come up from the vehicle acoustically about once a minute, and then we'd push that to shore. So the science team could run their algorithms and update the vehicle with a new location to go map. We also did a few very deep dives, almost to 6,000 meters, characterizing abyssal planing habitats. So we were able to collect some more surveys with bathymetry, side scan, and also taking some video footage of the seafloor as well. This is just an overall dive summary, dive to dive, but what I really wanted to point out was we had a dive where one of our thrusters flooded. So this knocked out one of our motor controllers, of which we did not have a spare for. So listen in your control system classes, because we operated for the rest of the cruise with 3 out of our 4 thrusters. So just a shout out to control systems there. A couple examples of our preliminary maps of the area, the crater area on the right. So this helps identify areas of interest for the subsequent ROV dives and ROV Hercules. We did some concurrent operations with them on this expedition. So we use a pipeline with MB System, which is an open source software for processing this multi-beam data. I'd also like to briefly mention some work with remote operations that was performed on this expedition. So there's a big push in our lab for this teleoperations, remote operations concept, which is more involved with the operational actions of vehicles versus telepresence, which is more meshing scientific expertise in real time to the ship. So we're looking at how do you actually operate the vehicle, push data, do watch standing, and these sorts of items ship to shore. We have some upcoming new research vessels, which are smaller scale, smaller footprint. So removing some people from the ship has benefits. Also being able to distribute senior level expertise across multiple vehicles at one time, having your shoreside person be the expert can also help with staffing and of course enabling a more diverse workforce as well. So we had some previous work in remote operations on some technology demonstrations on Nautilus the past few years. Here we wanted to integrate with Sentry because it has an existing pipelines and routine operations. It made sense to try to integrate into these established routines and see where the bottlenecks were. So we covered watch standing, data processing, pre and post dive checks, and also a big help was training new personnel. So it's hard to train new people out at sea in real time. They take up a bunk. So being able to push some of this to shore can really be helpful. And also to continue to monitor Starlink performance or lack thereof in various regions. So we can establish future baseline thresholds for what we can push for data and pull for data in real time. We had a partnership with industry for this work as well for DNAV. So there's an opportunity to learn from them. They had this sort of black box rack mountable remote operations sensor, which goes on board the ship, handles the VPN, so ship to shore network, had voice communications through an intercom system, and also video streaming through 4 ports. Some various hardware on the ship we used. So the intercom box on the left gave us very clear audio, ship to shore, low latency. We kept the remote operating sensor in our server van, very small footprint, about 17 inches across and 17 inches deep. We used tablets for our pre-dive checks and logbook, and also had headsets available for deck work. We talked to shore. So the time difference between American Samoa and the East Coast was around 7 hours. So it worked out pretty nicely that they could handle some of the overnight work. So we had sign-up sheets for these normal East Coast hours where they helped perform tasks that fell within those hours, or could also help with development and testing different network performance capabilities. We train new personnel, as I mentioned. And a big thing with this is trying to learn the workflows and con-ops to make this less awkward. It can be challenging on board to interact with shore if you have, say, long latency or awkward comms. So trying to make this more seamless and more workable so that shipside personnel are willing to embrace this technology. And again, identify the bottlenecks of how some things are implementing with this vehicle specifically. Some ways GUIs have underlying data structures, how data flows. Some of this can be slower for ship-to-shore collaboration. So thinking of ways we can work around this and also develop things to make that a bit smoother. To help also inform design decisions on future vehicles, which I'll get to in a moment. So on this expedition, we took over a terabyte of data, about 142 dive hours, roughly 300 kilometers of track line. As new sensors, we integrated a CO2 and methane sensor that was developed at HUI. So that's just an example of integration of new sensors on this cruise-to-cruise basis. We had the remote operations and real-time data streaming back to shore, and also the ROV concurrent work. So lastly, I'll mention some exciting future and upcoming work we have. We're calling this HROV, or mid-size ROV. So we received funding from both NSF and NOAA to build this new family of vehicles. These are going to be 2 4,000 meter rated ROVs. They're supposed to be small footprint, well instrumented, so that we can push some of the work to shore and be logistically easier to move from ship to ship. So these vehicles will be built in the next 2 years with expected sea trials late 2025. And a big thing for this with us is we're also collaborating and partnering with Green CIQ. So partnering with industry and using both of our strengths to create these vehicles. So there's a lot of people to thank and a lot of sponsors to thank, but thank you, and I'd be happy to take some questions.
I was curious, the plane wreck you're trying to find, what the notability of the Sloan Clipper was, like why that plane in particular?
I believe, so it was a Pan Am plane. I believe it's one of the first to do some of the trans-Pacific flights. There's a lot of information on the Nautilus website about the history, but I believe it's something about it was like the first male runner to really make that Pacific flight possible.
Is it any of those vehicles, do you also use optical sensors for doing photogrammetry as well?
So in some cases, we'll carry payloads with cameras that can do those sorts of things. We've also with NUI done some demonstrations with optical modems, so the communications through an optical modem, so almost like a wireless tether to another vehicle. So we've used some optical sensors before. I would say it's standard, but if a scientist has something they're developing, we'll stick it on there and use it.
How often do you have to calibrate the camera sensors on NUI? I saw you had like little checkerboards in the door.
Yeah, so none of us, like I say, are video experts. We mostly use the cameras for our own purposes for manipulation and being able to see where we are. So it depends on the scientists. Usually they'll do their own calibrations, depending on what they're trying to get out of it. Those checkerboards were from some previous work where scientists brought their own camera system that we integrated, and they were using that for some like 3D visualizing of the workspace and some like autonomous manipulation and things like that.
Your fiber optic cable, thank you, by the way, very nice job. Fiber optic cable is so thin and fragile, but you send out 20 kilometers or something like that. Is that why you keep it thin? Because the drag and so forth?
Yeah, so the drag issue, and just like a space issue, is even just wound up, they're still pretty hefty
How
cameras.
often do you break? How often do they break?
Well, we were in the Arctic last year. We had 6 dives and it never broke. We saw some degradation occasionally. Sometimes it came back, which was amazing because we were 6-7 kilometers away from the ship at times. So it's pretty strong tensilely. And unless we see sometimes once it gets to the seafloor, it'll get snagged on something, or we have a joke that the crabs get to it once in a while, and that will break it. So a lot of times we'll kind of see the bends in the traces if it starts to get snagged on a rock or something sharp. But especially when we're, I say, deeper and the environment's less dynamic too, we have better survivability. Whereas like this past cruise in Greenland where there was a lot of sediment moving around, a lot more dynamic, we lost it, I want to say, I think 2 out of the 8 dives. But it was like further into the dives, we were almost at the end. So they survived almost the entire dive as well.
And it just comes back, homes it back to where it's supposed to go when it can't communicate with you.
Yeah, so once the tether is lost, usually we program it, so I'll usually like hold station, and then from there we see if we can establish comms with it. If so, we can say do a multi-beam survey or do a track line home if you only have X amount of battery. So it's kind of situationally dependent, but if it doesn't hear from us for whatever reason, then I'll kind of take that track line home. Or some of the cases where we were worried about how it would navigate out of the glacier, we would just define a heading and thrust value. So if it didn't hear from us, they just head some way for some amount of time until it got out of the danger zone.
Mhm. Crazy, yeah, interesting, yeah.
So there's no armor at all on the fiber cable?
No, we do work with some in the lab for some other projects that do have armor to them, but this one's completely bare.
So it gets scratched, doesn't it?
Yeah, so that can also, we find that its survivability is very good, but yeah, you can nick it. And those are sorts of things where we might see it degrade and we'll see the bends, but we still have enough margin that we can still communicate. So it doesn't have to be perfect. It just needs to have enough margin where we can still have the comms to the vehicle.
And do you swap it regularly? Like if you see it starting to degrade?
Yeah, so there's various conditions for swapping it. So it's basically it's disposable, so we aren't able to re-spool it. So whatever comes out is out. We have to remake some of the splices dive to dive. But also we'll see like if there's some corrosion or it seems a little crusty, we'll swap it out. But as you can imagine, those canisters are pretty expensive. So we go through some number of them each cruise, and definitely an expense.
How are you able to like realistically inspect that length of cable once you bring it in?
Yeah, so we can't physically inspect it, but through those OCDR traces, we can shoot both ends and really make sure that it's a clean trace. So if we see anything in that trace, we'll replace it.
Do you do those tracers like when it comes back? Or can you do those in real time?
Those are in real time when we have the fiber intact. I think it's like once a second we get an image.
How costly is that fiber?
Scale of tens of thousands.
How hard is it to swap the batteries out during operation?
Not something we want to do. So there's 3 big boxes and they're sort of at the center of the vehicle. So it involves a lot of like maneuvering and taking things off. And we have like a specialized contraption that makes it a bit easier to get them out because they're really heavy and they're full of oil and they're just like not fun to work with. But they work well like depth and there's not much out there for options in terms of like those sorts of batteries and endurance. They're capable of going that deep. So definitely not something we like to do. And most, we haven't had to take them out on the past few cruises. They have before, but. Not
So you can keep them on board to recharge them or?
Yep, so we have charge cables. We carry 3 large power supplies. And we have 3 in parallel and.
Somebody else doesn't have. So you mentioned before flow that comes out of the glaciers themselves from melting water and so forth. Did you detect that on these cruises? Or were you able to identify flow coming out of the glaciers that you could attribute to melting?
Yeah.
The second question is at what velocities can your ROV operate safely?
Yeah, so the first question, I'm not as familiar with what the scientists were processing, and they're still processing, but I know they were definitely excited about some of the flows they were seeing with our vertical transects, and just sort of the inflows and outflows and the magnitudes of which they were seeing they were very happy with the data they were collecting, at least in real time. But they're still working on the processing.
Do you know what those magnitudes were? How fast are the flows under the ice? Like, or when these places where you might have a mix of fresh and.
Yeah, I want to say a meter per second. But don't exactly quote me on that.
Significant.
Yeah.
Yeah.
There's the effort, like we could tell with sort of our commanding thrust to the vehicle, just how strong they were pushing for us to, for the closed loop controls to actually handle those. So the vehicle itself, in terms of what it can handle in terms of current, yeah, it depends which way. We have a lot more forward thrust than aft thrust and side thrust. So if we're facing the right direction, we can do very well, a meter or 2 per second. But it just takes a lot of power consumption too. So we see the battery drain faster and some things like that we have to consider.
More. This is the question for you. You have another affiliation also with ocean engineering, right? You're on the board of the undergraduate program, are you?
Yes.
She's an external board member for the Bachelor's of Science in Ocean Engineering.
Good one has to be on land this year for the meeting.
Yes, she's often at sea when we want her to come, but yeah, so maybe we'll see you again in the spring or other times, yeah.
We travel a lot, but I think, I don't know, that whole like being on a team next to the middle of the night, you're trying to recover this vehicle. It's like just a lot of, I guess, dynamic environments you put yourself into. And also just the troubleshooting with that team, like you are the only people on the ship and you have only these spares and these things to work with, and you have to find a way to make it work.
Did you expect it to come out the way you did? Like when you graduated and left and went there, did you know what you were getting into? Or did it pleasantly surprise you?
Yes and no. Yeah, so I think I've been fortunate to be involved with a lot of different projects and really interesting projects and being exposed to a lot of different things. So just what I was working on during my graduate work isn't necessarily what I do now all the time, and that's okay. So what I learned during graduate school was definitely applicable and just gave me a really good background how to perform research and troubleshoot and just critically think but have also learned a lot in the past 3 years with the hands-on work and just being in the environment and putting my hands on these vehicles and working with them.
Any other questions? Will everyone give a hand for Alyssa?